Geometry is a very heavily vocabulary intensive math. We have a lot of definitions, we have a lot of theories, we have a lot of postulates. A postulate is what I like to call like a no-brainer. It's a statement that is accepted as true without proof. We don't have to prove it. Let me think. Okay, I don't have to prove to you that the sky is blue, right? Like, so if I came up and I just said the sky's blue, you would accept that as true without proof. That's kind of the idea of a postulate. They make sense. You're just like, oh yeah, that makes sense. So you don't have to prove it. Like I said, we live in 3D, so we can see 3, 2, 1, and no dimension, or we can conceive of those. We can mathematically conceive of higher dimensions than we live in, like 4, 5, 6, 7, 8 dimensions. They go on forever, but we can't see them because they're beyond us. A point is 0-dimensional because it has no shape and no size. If you were to try to think of the smallest particles that make up an atom, you guys have heard of the subatomic particles that are so small we can't actually see them, we can just theorize about them. That would be a point. It's a location in space. They exist in 1, 2, and 3-dimensional space because they have no dimension themselves, so they fit inside. And we represent them by dots. But it's much smaller than this. And the reason they can fit inside larger, they fit inside lines and planes and spheres and things. Smaller things can fit inside larger things. You can't fit a sphere inside a line, but you can fit a line inside a sphere. Kind of that idea. Make sense? Yeah, it's represented by a dot, just a dot. A line is 1-dimensional. Okay. It is made up of an infinite number of points. Points has an I in it still. And that goes in 2 directions. So basically you take these points that are teeny tiny, infinitely small, and you take an infinite number of them and you stick them together in a big long string. And they go on forever and ever in 2 directions. And we draw or represent a line by making like a little piece of a line with arrows on the end to show that it goes on forever. Okay. Both points and lines are considered to be undefined. Okay. And the reason that they're undefined is because we can't technically define them, but we can describe them. Sort of like a person. You can't define a person, but you can describe them, right? Does that make sense? Okay. All right. A plane is another collection of points, except instead of just going in 2 directions and making like a string that goes on forever, a plane is like a piece of paper. It's flat, but it goes on forever and ever and ever. So if you could take a piece of paper and extend it out in every direction, it just kept getting bigger and bigger and bigger, and it would just never end. That's what a plane is. It's flat though, completely flat. A plane is 2-dimensional. And the dimensions are based off of how many axes you have. You guys remember the x and y axis in algebra when you were graphing? point has no axis, so that's why it's 0-dimensional. A line has one axis, 1-dimensional. And a plane has two axes, like your x and y axis, so that's why it's 2-dimensional. And then when we get into 3 dimensions, you end up with 3 axes. So then we have the words collinear and coplanar. Co means together. Cooperate means that you operate together. So collinear are points that are together on the same line. Coplanar are points or lines that are together on the same plane. And then the opposite of those, you would just add a non in front of it. So you can be collinear if you're on the same line, and if you're not on the same line, you're non-collinear. If you're on the same plane, you're coplanar, and if you're not on the same plane, you're non-coplanar. To think about coplanar, if this floor is a plane, we're all coplanar, because we're all on the same floor, right? But the people downstairs would be non-coplanar, because they're not on our plane, they're on the plane below us. Just a sec. All right, so far we had points, lines, and planes, and those were undefined. They're just described. Space is actually defined, and it is boundless. When we talk about space as a geometry term, it's kind of the same thing as outer space, where it goes on forever and ever, and it never ends, and it's in all directions, right? It's 3-dimensional, and so when you have your axes, and this is the best for drawing, but I have my x and my y axis normally. The third axis goes straight through. So I can't obviously draw that very well because I'm drawing in 2D, a 3D thing. But if this pen were to go straight through the board and keep coming straight out, that's the third axis. So you can, yeah, 3D. When we're naming lines and planes, there are very specific symbols that we use, or terminology, or letters that we use. If you look at this little N here, you'll see that there's no dot. So that's indicating that this line is called N. And this R has no point, so that's indicating that this line is called R. And this P in the corner has no point, so that's indicating that this plane is called P. So if you see a letter associated with a line, it's italicized, but it's kind of hard to see with this particular font, unfortunately. But it'll be italicized, lowercase letter, no point. That's the name of the line. And a capital italicized in the corner of the parallelogram, we represent planes with parallelograms. That's the name of the plane. That's not the only way to name them, though. So we can talk about a line containing point W. That's this line here. We can call it line N, like that. But we can also name it with any 2 letters that are on that line. So we can use any 2 letters. Now, the reason we have to use 2 letters is because it takes a minimum of 2 points to define a line. So we have to use at least 2 letters, or we use exactly 2 letters to name lines. And the symbol for a line is the same as how we draw it, a little double arrowed line segment, and you put the 2 letters underneath. So I could call this line VW, because V and W are on the line. I could call it WX. I could call it VY, VX, XY, WY, And then I could flip all of those letters around, and it could be WV, XW, YV. So there are a whole bunch of right answers if I tell you to name the line.
So even though it's called line N,
It has multiple names.
because it has all those other
Points on it, yeah. So you just any 2 points on the line with a little double arrow line over top of it, and you've got a correct name.
So you can pick whichever.
You can pick whichever one you want. Kind of the same thing with a plane. This plane is named plane P, so we can call it that, plane P. But with a plane, you have to use any 3 letters. Because it takes a minimum of 3 points to define a plane.
X, Z.
I could use X, Z, and Y. So I could call this plane XZY. I could call it plane WVX. Just any of these letters here, I can use any 3 of them.
But you have to write the word plane in front of it?
You have to write the word plane in front of it. There's not a symbol for a plane. Because we use a parallelogram to represent a plane, that kind of causes a little bit of an issue. Because if I were to draw a parallelogram and put some letters in behind it, this says parallelogram, whatever that is. So I can't use the parallelogram as a symbol for the plane. So we have to just write the word plane, unfortunately. Yeah, that happened a couple thousand years ago, so I don't think they're willing to change it at this point. Let's see. Euclid first collected the first anthology of geometry and collected all known information about geometry in 300 BC. So let's see, it's 2014 now, so that's 2,314 years we've been using the word plane.
So for a line containing point W, you have to define it with 2 other points, right?
One for the line, you need 2 points.
To define it
as a line.
As a line.
Yeah. So and it can be any 2. It can be V, W, X, or Y because those are all on the line. So you can use any 2 of those letters. For the plane, we have to use 3 of the letters. And if we look at the plane here, I can't use T because T is not on there, right? T is out here in space. But I can use Z, Y, X, V, and W because those are all in the plane.
What's N?
N is the name of the line. It didn't have a point, so it's not a point. Does that make sense? It has to actually have a dot. Yeah, it has to have a dot to be a point. If I throw a random letter here, wait, I don't want to use X, I already used X.
So we can't use P.
No, it has to have a dot. Because if I throw a random letter here, like let's say I throw a random Q right there, I don't know anything about that Q because it doesn't have a point on it. So I have to just ignore it.
Q plane?
No, the plane is always in the corner.
Okay.
We always put the name of the plane in the corner. So if you just have random letters floating off in space,
So
you sort of just ignore them. Yeah.
The plane actually doesn't have to be D, it can be like R, the name of the plane.
It could be if this was an R.
Okay.
Yeah. Yeah, whatever letter basically is alone in the corner with no dot, that's the name of your plane. And or any 3 of these letters that are in the plane that have dots. All right, now if we look at this, we have a plane containing points T and Z. T's up here, right? You see that?
Yeah.
And Z's over here. So I would need a plane that kind of, can you see the yellow? Sort of comes around like this and then maybe makes a, some sort of like this happening thing, right? Does that make sense? So now in order to name it, T is on line R, Z is not. To find my 3rd letter, I have to have either a letter that is on line, that's on the same line as T or on the same line as Z. There's no line coming through Z, right?
So would X,
So I'm going to use X. So I'm going to call this plane TXZ, or I could call it TZX or XTZ. The letter order doesn't matter on these. So in some areas of geometry, the order of the letters is going to be really important, but not in naming lines and planes. When you're just naming lines and planes, it doesn't matter what order they're in. Okay. Darn it. Sorry, I saw my spelling error. Okay, a line containing T. So I've got T and X are on this line here. So what can I call this line?
TX, R,
Yeah, I can call it TX with the symbol over it. I can call it line R. I could also call it XT if I wanted. The technical definition of an intersection is the set of all points that two geometric figures have in common. Basically, all this means is where they overlap or hit. Okay. An intersection is always going to be the same size as a geometric figure, the smallest one, sorry, the same size as the smallest, or less. You can't intersect and become bigger and have a bigger set of points than you started with. Does that make sense? So if I have two lines that intersect, this is the intersection and it is a point. Okay. Right there. Two lines can intersect at a point or a line. And the way you would get two lines intersecting at a line is if you had one line and then you had the other line that was like right on top of it. So this, I can't even draw that. Hold on one sec. Basically, if this was actually two lines, that's how you have an intersection that's a line. If you have two lines and they're just perfectly on top of each other. Okay. With a plane, if you intersect two planes, you get a line. This is two planes intersecting. And then if you get a plane and a line intersecting, you get a point. Now, you can have a line intersecting the plane flat. Sort of like if this pen was my line and this paper was my plane, they're intersecting like flat, so they make a line. But what I can't get is a line and a plane would intersect and make a plane, because the line is never going to get bigger than it is. I can have two planes intersect and make a plane, where if I have these two pieces of paper and they lay on top of each other and they're intersecting planes, so they make a plane. but I can't have two planes intersect and make a cube. It can't go bigger. It can only stay the same size as it is or go smaller for the intersection. Okay. Are these pictures okay? I mean, as far as the clarity of what's happening there? A really large part of geometry is going to be able to take written information and turn it into a picture. Part of that is because if you can draw the picture and label the picture, it makes doing the problem much easier than just trying to take the words and turn them into a problem. So what we need to be able to do is we need to be able to interpret these words and turn them into a picture. And so what I have is I have line A, B, and C, D, and they're intersecting at a point E. I have points A, B, C, and D that are on a coordinate plane. And then point F is coplanar with these points, but not collinear with either line. So what I need to do first is I need to take this information that is for sure given. I know the coordinates of these points. So I'm going to graph those points first. So A is -2, 4. Actually, so I'm graphing my points. This is point A, so I'm just going to label it. Point B is at 0, -2, so I'm just going to label that also. And I'm going to go ahead and draw my line because I have line AB. So I know that A and B need to connect. So there's my line AB. And then I'm going to do point C, which is -3, 0, and point D, which is 3, +3. So I'm going to go ahead and label those. And I'm going to draw my line. Okay. So now I have lines A, B, and C, D drawn. The next bit of information, we're intersecting at E. Now, there should be a T there. So wherever those two lines intersect, I draw a point and I label it E. Because I was told that the intersection is E. The last bit of information that I have tells me that F is coplanar, but not collinear. A coordinate plane is a plane, right? And these lines are on the plane. So I need to put some point F somewhere on this plane, but make sure it's not on either of the lines because it's coplanar, but not collinear. So I can put F anywhere, right? Because I've not been given any specifics other than it needs to be on the plane, but not on the line. So I could put F here, I could put it over here, I could put it anywhere I want. Anybody have an opinion as to where F should go? Except tell me when to stop.
Stop.
Okay. There you go. There's not going to be one specific right answer for F. The only wrong answer for F would be is if I put it on a line. It can go anywhere else. That's the part that you have to look at. Okay, so planes. Plane T. Plane T, we're going to draw a parallelogram. Okay, we haven't really gone over, you guys should know parallelogram is a rectangle, but then you kind of smush it sideways. And it does not have to be a pretty parallelogram, just so long as you draw something relatively parallelogram-ish. It's not really a word. Or if you're like me and you like to cheat, you can draw this kind of ugly parallelogram and then the computer will fix it for you. Don't worry, I don't grade on pretty. Okay, plane T. So we need to name this parallelogram T. So we stick a T in the corner with no dot. Okay, so that's plane T. Now, we need a line QR to intersect plane T at point S. So if it's intersecting at a point, that line needs to punch through the plane, right? Does that make sense? So what we do is we draw a line, and at some point in the plane, we switch to dotted. This dotted indicates that that's now on the other side, it's gone through. And it can go anywhere in the plane. You could have drawn it over here. You could make it sideways, like angled. Yes.
Do you also have to draw a QR?
Yeah, so at some point you switch it to dotted. At that point you switched it to dotted, that's the intersection point. That's S. And it's a line, so we need to put arrows on both ends. And it's a line QR. So now we need to put a Q on there and an R on there.
So it's going to intersect S to the point. So the line QR will intersect.
Yeah, so that because this is line QR, we need to put the Q and the R on it. And where the Q and the R go don't matter. Okay, so S, they just have to go somewhere on the line. S has to go at the intersection. That, we named that S as the intersection, so it has to go there. Q and R can go anywhere on the line. Now, typically, I put them at like the ends. Just me, that's me personally. But you don't have to. I could put R right next to Q if I wanted. Or I could put Q over here by S. It doesn't matter. Just so long as Q and R are somewhere on the line, S has to be on the intersection. So I didn't put a coordinate on here, and let's say I don't have any graph paper. I want to draw some axes. Okay. And then I'm going to just put some relatively equally spaced hash marks. Okay. So I've got to go to J, which is at -4, 2. So 1, 2, 3, 4, 1, 2. I'm going to call that J. And K is at 3, 2. 1, 2, 3, 1, 2. Call that K. I'm going to move my J, actually. Make it a little closer. Okay, so points J, K, and L are collinear. I don't know anything about L. What I do know is that I need to make a line through J and K. And because I haven't been told anything at all about L, it could go anywhere on the line. I can put L in front of the J, I can put it between, I can put it over here to after the K. Doesn't matter. It just goes someplace on the line. So they just need to be on the same line to be collinear. And finally, we're going to have line P in plane N containing point L. So I'm going to start by drawing my plane. So I'm going to draw a parallelogram, and again, my computer's going to fix it. Okay, the plane is N, So I put my N in the corner. I need a line P. Yeah, now it's lying in the plane, which means that we need to keep it all, it doesn't go through, it's on top of. So you keep it in the plane like that. And we're going to call it line P. It doesn't have a point, so it's line P. And it contains point L. And put point L anywhere just so long as it's on the line. Does this pyramid have, and that's going to tell us how many planes are just in the pyramid. Yeah, so we've got 6 sides, right? And so 1, 2, 3, 4, 5, 6. So that's 6 planes. And then we have this plane here, so that's 7. Now, this one we can name X, because the X is in the corner.
There's 7?
7. We have the 6 sides of the pyramid, and then the plane that it's sitting on top of.
Okay.
Okay. And then the base of the pyramid is part of the plane that it's sitting on, so we don't have to count that.
Okay.
So we have plane X, that's this big parallelogram plane. Mm-hmm.
You don't count that plane because it's already sitting.
Yeah, because it's if it's intersecting, so it's part of the same plane. Yeah. And then we have each side. So we're going to start with this one. So I've got plane JHD, and I could call that HDJ, DJH, whatever, right? I just need those 3 letters. Doesn't matter what order they're in. And then I have J, K, and D. And then I have D and K and E. That's this part right here. And then I have this side that contains E and F and D. The one with G, F, and D. And finally the front, which is the H, G, and D. So I've got 1, 2, 3, 4, 5, 6, 7. I got them all. So far, okay? Right. 3 points that are collinear. Well, this line only has how many points? 2. These all have, well, if you go around this way, these aren't collinear because it makes a hexagon, not a line, right? So that,
J, C, D.
yeah, we've only got one line with 3 dots on it. So J, C, and D. Okay, we're going to name the intersection of plane HDG with plane X. Okay, HDG is this front right here. I'm going to, for now I'm just going to highlight it. Do you guys see that HDG? Where is this intersecting plane X? Plane X is the floor, essentially. HG. Oops, pen, not highlighter. And the intersection of a plane and another plane is going to be a line, so we're going to call that line HG.
It wouldn't be HD because D
The HD is going up, right? So it's only H and G is where it's intersecting the floor. D is out in space. Mm-hmm. Okay, at what point do line AB and line EF intersect? Well, we don't kind of really know, do we? So what I'm going to do is, if this was your paper, what I would recommend you do is you take a ruler and you would extend out this line and kind of see where it intersects. Oh dear, I drew it wrong. It's supposed to intersect there. I was copying this out of the book, so I don't think I lined it up quite right. This should have been more over here. So it should have intersected at point B. But since it didn't, well, okay, you know what, that actually, this is legitimate. Like, okay, so we take our line, right? And it doesn't intersect it anywhere that we can see. So we'll just say no intersection.
So if it did intersect, what would we put?
We would put the point where it intersected. So if it did intersect at a point, we would say what that point
Yeah,
was.
if there was a point.
Yeah.
Okay.
So there was no point?
There's no point. Okay. Our points E, D, F, and G coplanar. We have E, F, and G, and D. So are they all on the same plane? Can you tell by looking at that? E, F, and G are on plane X, right? G, F, and D are okay. E, F, and D are on a plane, but are all four of them on the same plane?
No.
No. So they're not coplanar. Okay, and then at what point or in what line do planes JDH, JDE, and EDF intersect? So I've got J, D, H, J, D, E, and E, D, F.
D?
D. Yeah, they all have point D in common.
Could you just look at?
The letters.
Okay.
Yeah. Just I wanted to show a picture though.